famous physicist Schrödinger. He's still alive, and he's in my Discord channel, and he asked for help with solving Laplace's equation. And me, being a good fellow physicist, I can't turn down someone like Schrödinger a request like this. So today, I'm going to show you how to solve Laplace's equation using very, very simple techniques in Python. We're not going to do some big for loop or some quadruple for loop to solve this. I'm going to show you how to solve it using a convolution. We'll deal with a problem that has complicated boundary conditions. We'll have places of fixed potential and also places of fixed charge. This is a combination of Dirichlet, I think, boundary conditions, I'm probably saying that wrong, and also Newman boundary conditions. And implementing these both at the same time is actually really easy in Python. As always, like and subscribe if you enjoy these videos. I'm sure you'll get something useful out of this channel in the future. And join the Discord server as well. We're almost at 1,000 people now. The number of packages you actually need to solve this problem is very few. I just have NumPy and Matplotlib, which are the essentials that I basically always use. And then SciPy, the image processing library, I have Convolve, which you could really do with NumPy. I just like this one a little bit more. It's a bit easier to use. And then also generate binary structure, which is going to be used to form the kernel. That's the thing that we convolve the image with to do iterative updates for Laplace's equation. So I think the easiest way to summarize Laplace's equation is as follows in E&M. Given that you have no charge in space, you have the Laplacian of V is equal to 0. And then you basically have two different types of boundary conditions. And the types of boundaries I denote as omega 1 and omega 2. So the first here, this is known as the Dirichlet. I'm probably not pronouncing that properly, but I don't really care. Dirichlet boundary conditions. And these are where the potential at certain points in space is fixed. So the potential is set to maybe a constant value, or maybe it depends on space, but it doesn't change. And so in the image below here, I have the blue region representing omega 1. That's this sort of region here. And these are regions of fixed potential, so these are like conductors. And usually they're held at a constant potential. So this might be held at like 5 volts, this might be like 3 volts. Maybe up here you have 7 volts and 11 volts. So these are the places of fixed potential. That's the first sort of boundary that you'll encounter. And these are conductors. You also have another sort of boundary condition here. And it might look confusing. I have dV, and this is omega 2 region. dN is equal to 0. And omega 2 is the gray region on this diagram here. And so this represents insulators. And with an insulator, you have no electric field flowing inside the insulator. What that means is because the electric field is the gradient of potential, right? If I take the derivative of potential going into the insulator, if that derivative is positive, it says that there's electric field going into the insulator. But I don't want electric field going into the insulator. That's a property of insulators. They don't have electric field going in them. So that says the derivative of the potential with respect to the normal vector going out of the insulator, so you see that here, you see that here, you see that here, is equal to 0. This enforces that you have no perpendicular component of the electric field at these surfaces. So that's true when the fixed charge on the insulator is equal to 0, which we're going to use in this case. And so these are insulators. And so basically, there's conductors, there's insulators, there's a lot of materials in between. But in a very basic way, and in most problems in the real world, basically these are the two boundary conditions that you have. You have conductors and insulators. And you can combine the two boundary conditions if you have more complicated scenarios. But in most cases, this works fine. So let's focus on the actual equation. Laplacian of V is equal to 0. In 3D, that's just given by this here. You expand this. I'm sure you've seen this in courses that you take. Now, we want to make this discrete because we're going to solve this equation on a grid of points. This is 2D, by the way. We're solving it in 3D in this video. So basically what that means is we can approximate the second derivative like this. So I have indices I, J, and K that you can see here. I represents where we are in X, the X sort of voxel position. J is where we are in Y, and then K is Z. So we have 3 different positions here. And the second derivative at a given point, ijk, so this is at a point ijk, is approximately equal to vi plus 1 jk minus 2 vi jk plus vi minus 1 jk. So you just take the voxel sort of representing at position ijk, 3-dimensional space, and you go sort of x minus 1, x plus 1, and that's sort of this point here, the potential at this point here, minus 2 times the potential at the actual point. And you do that for x, y, and z, and you get this discrete equation. So this is true in Laplace's equation. And our solution v to the problem we have will satisfy this equation. Now, if we use delta x equals delta y, there should also be a delta z. These are all equal spacing in our 3D grid of points. We can actually solve for vijk. You'll note the vijk shows up in all these different expressions. So we set delta x equals delta y equals delta z. We could just multiply by that, bring it to the other side, we get 0. Then we solve for vijk, and we get the vijk is 1/6 of all these points. So I plus 1, I minus 1, j plus 1, j minus 1, k plus 1, k minus 1. So it's basically the voxel. It's all 6 voxels. Remember, you're in 3 dimensions here. You're in the center. You have one above, one below, one to the left, one to the right, one in the front, one in the back. And it says that the potential at any given voxel is the average. That's what this is here. The average of all the potential of the voxels surrounding it. This is like the averaging. I think it's called the sifting property of Laplace's equation. But this is like something that holds. When we're done solving our problem, this will necessarily be the case. That's why I say it's a property of the true solution. But when we start, we don't know the solution. We know when we solve it, this will be a property, but we don't know how to get there. Well, there's an idea. And the idea is to repeatedly set. So you come up with an initial guess of the potential at all points in space. And so someone said, well, what if I take vijk and I repeatedly set it equal to the average of all the points around it? So you have your initial guess, then you take every point and you set it to the average of all the points around it. And you do that for every point in the array. And you do that over and over and over and over again. Well, you know, it's not intuitively the case that you might think it's true, but it is true. And you can mathematically prove that if you do this enough times, the potential will settle to the true solution that you will get for the problem. So it's not easy to prove to yourself immediately why that's true, but it is true. So this is a property of the true solution, and we do this over and over and over again, and you'll eventually get this property. So again, the hopes is that v will get to the true solution, but it's mathematically proven that it will. And so to do this, we want a good initial guess for the potential. So we'll set an initial guess, then we'll apply this formula over and over and over and over again. Eventually, the potential will settle to the true solution. So you saw this diagram here. The problem we're solving today looks like this. We have an insulator on the boundary, sort of like this. So the electric field does not flow through here. That's why I have this derivative here. And we have a conductor set to potential V0 and a conductor set to 0. And this is a 2D cross section of what we're actually doing. In 3 dimensions, you can imagine this sort of growing out like this. We have 2 conducting plates surrounded in an insulating box. And by the way, this insulating box is a good approximation for infinite boundary conditions, which you can't do on a computer. That says that the potential is 0 at infinity, and you'll get a sort of the potential here. So, but also there are cases where you might construct a physical device, a capacitor, surrounded by an insulating body. And this is a good way of getting what the sort of fringe fields are. If you've taken an E&M course, you've probably solved for the potential between 2 infinite plates, one at one potential, one at the other. It's not very hard to do. But as soon as there's this and you get sort of a fringing field pattern where the electric field kind of goes like this, and then it's obviously straight in the center, it's not able to be solved analytically, but you can solve it numerically, like in this example here. And so we'll be in 3 dimensions. So first we'll come up with the grid for our potential. And rather than solving del squared v is equal to 0, we're going to normalize by v0. So we'll solve this problem here. That means I can just set this equal to 1 and this equal to 0. And that keeps the problem dimensionless, which I always like to do in these videos. And you'll note if v solves this equation here, then it also solves this equation. So it's okay to do this. So we're going to use a 100 by 100 by 100 grid. It's a fairly big grid. That's 10,000 times 100. So I should know this quick. That's 1,000,000 points, I believe. 10 to the 2 times 10 to the 2, 10 to the 2 is 10 to the 6. That is indeed 1,000,000. I'm great at math. And so I have n is 100, and I'm going to set the grid, all the points in the grid, the potential equal to 0.5 to start, even though I have 1 here and 0 here. So that's how I'll start. And now let's set the location of the parallel plates. These are going to be fixed throughout. Remember, we do that averaging procedure over and over, but this always stays fixed. So So this always stays fixed, even though we do the averaging sort of in the white space here. And also the derivative equal to 0 always stays equal to 0 at these points. So we have to apply the boundary conditions after we do this. So this is like the first step, then we apply the boundary conditions. So for that, I need the location of the grid. Well, I'm going to go from 30 to 70. So it goes from 0 to 100 points. I'm going from 30 to 70. So it's a length of 40. So you have 30 on each side. And it's just a square. So I set my grid. I go 30 to 70 in X, 30 to 70 in Y. Remember, between 0 and 100. So this is just a little square. And then 20. So it's a little bit above the insulating box as well. I'm setting that equal to 1. That's V over V naught equals 1. And I'm setting the bottom one here, which is this grid here, equal to 0. It's got the same sort of dimensions as the other plate. And then I need to know what location this is at. So I call this my mask, positive and negative. This is an array of Boolean values. So if I run this, if I run all my cells here, and I'll show you what I'm doing. So I have my grid. It's just a 3D array of all 0.5s right now. And I set the certain locations equal to 1 and 0, and then I get my positive and negative mask. And so my mask positive will be a bunch of trues and falses. It's mostly false, but it's true at the location for positive at this location here. So it's a 3D grid as well, and there will be true all at the location of that positive potential grid. Same thing with my negative potential grid. So if I plot.imshow this, and I mask positive, and I just take the z equals 20 slice, which is where I set it equal to 1, you'll see that it's equal to 1 here. But at all other locations, like z equals 19, there's nothing. Z equals 21, there's nothing. Everything else is 0. So by the way, yellow is equal to true when I plot the Boolean array here. So you can see that this is sort of equal to true at this location. And my mask negative, which gives me the locations of my fixed plate of equal to 0, that should be true at 80, right? And then at 81, it's not, right? So it's only true at the locations of those grids. And I have one for the positive plate, one for the negative plate. Okay, so I set my mesh grid like this, and it's a weird order, but it goes Y, X, and then Z if you want to keep things consistent. Now, what a mesh grid does is it returns 3 3D arrays in this case. And each 3D array you could think of as like the information at each voxel tells you what's the value of either Y, X, or Z that you're at. So if I run this cell and I look at XV, it sort of looks like this. If I take my index 0 and X, that first bottom, or I guess like this X part, everything is equal to 0 because it says no matter where you are, like in Y or Z, I'm always at X equals to 0. But if I take, this would be the Y equals 0 slice, you'll note that X sort of repeats along columns. That's like this. And it says X is equal to 0 as you go along this column. X is equal to 1 as you go along this column. X is equal to 2. So if X is like this, everything is equal to 0. But if I take a slice like this, then it's always X equals 0, X equals 1, X equals 2. And it sort of works like that. So that's what a 3D mesh grid is. And I can use that to construct an initial guess for my grid. And if you look up here, you imagine it's going to be high potential here going to low potential here. So what I do is I just use a linear approximation. I say the grid is equal to 1 minus ZV over 100. And if I look at my grid, so I can just make a quick contour plot of this. And I'll take let's look at the X equals 0 slice. So in that case, I have Z going in this direction and Y going in this direction. And you can see that these contours get brighter to darker. So the potential is high on this side of Z, getting darker to this side of Z. It should be the same thing if I take a Y slice. Z's pointing like this, but now this is the X direction. So it says that the potential sort of gets lesser, lesser, lesser as I go like this. And that sort of matches up with this diagram that I have here. So now that I have my initial guess for the potential, which by the way isn't very good, but it gives a good starting point for applying this algorithm here. And I'm going to add a K here because this needs a K. And so we need to apply this over and over and over again. So the way to think about this is in terms of a convolution. The fastest way to do this is with a convolution. And you might think, how the hell is this a convolution? Well, consider the following example. In 2D. So suppose I was setting Vij rather than the average of all 6 blocks surrounding it. In 2D, right, there'd be 2 on top, 2 on the left and right. So it's actually 1/4 of all these points. So consider this example, and suppose that this is sort of a region in a big 2D array, and I'm at point 5, which is Vij, and these are all the Vi, this would be Vij plus 1, Vi plus 1j, Vj minus 1i, etc. And so we want to know like what exactly is going on here when I do this operation. So the red box represents Vij, that's 5, and it's going to be updated in the next iteration. And the purple boxes represent all these sort of points that I need to take the average of. So what I do is on my next iteration of this grid, I say, well, this point that's initially 5, it's now going to become 1/4 of 1 plus 2 plus 6 plus 7. That's my next iteration. And so this 5 becomes, it uses the information from these surrounding points like this. So it occurs for every pixel in the array. The same thing will happen to 6. 6 will become the average of 1, 5, 9, and whatever's on the left of this here. Note that I don't use 4. Even though I update this to 4 in the next iteration, when I find the newest value for 6, I'm still using the old value, which is 5 here. So 1 plus 5 plus 9, the average of 1, 5, 9, and whatever's on the right here. And this occurs for all pixels in the array. So this is a big array of like many, many pixels, but this operation here is a convolution with this matrix here that has 0, 1/4, 0, 1/4, 0, 1/4, 0, 1/4, 0, sort of like this. And that's because if I take this matrix and I sort of put it over top of this, and I multiply the two together, sort of element-wise, and I sum them together, which is what a convolution essentially is. A convolution is like the integral of this and this here, but really it's a sum because it's finite. So I take this and I overlap it with this, and I sum the multiplication of all the different elements here. I get 1/4 of 7 plus 1/4 of 6 plus 1/4 of 2 plus 1/4 of 1, which is the average of all these elements. So if I convolve this with this big matrix here, the next point, this point here, 5, will become the average of all these points. So all I need to do is take this big matrix here, convolve it with this matrix here that gives a new point at the center, and suddenly I have my entire algorithm, this operation here, of course it's going to be in 3D, done. So I don't need to worry about iterating over all the elements. So in 3D, the analog is this matrix here, which I use this kernel, and I use this generate binary structure. This is basically generates trues and falses, and it generates a sort of a true, and it does it so there's a 1 on top, and then all of them in the middle, like this. So true, 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 true on the main sort of rows, but false on the off diagonals, and true in the middle. And what I need is this center one false, because in this matrix, you'll note that I'm not actually using 5 when I update 5. So I just set that equal to false. Kernel 111 equals 0. And I also make it as float type. So if I take it float, it's just like 1, 1, 1, 1, 1, 1. I divide by 6. So I get 1, 6, 1, 6, 1, 6, 1, 6. And then I set the center point equal to 0. And I get the following array like this. So I need to convolve this with my 100 by 100 by 100 array. And that is essentially performing the operation I need. So I also need a function to set dv/dn equal to 0 at the boundaries. That's the insulator boundary conditions. So the function works really simply. Basically, at the x equals 0 boundary, for example, it sets v0jk as v1jk. You might think, why am I setting why am I setting this slice equal to the slice right next to it? Well, if dv/dx equals 0 at this boundary, which is true, this is equal to delta v over delta x equals 0. And by setting these two equal, I get delta v equals 0. And if delta v equals 0, the derivative also equals 0. So that enforces that the derivative equals 0 at all these boundaries. So it says that my x boundary is equal to the point next to it. So the derivative is 0. It enforces that when I'm performing this algorithm. Same thing on the right side of x. It says that this slice is equal to the slice next to it. So, and the same thing with y and same thing with z. So the derivative is forcibly always equal to 0. And I'll apply this to my array throughout the operation. This function basically implements the updating of the grid. So it's a for loop, and the for loop is how many times do I apply this operation. And the better initial guess I have, the less times I need to apply this operation. And so I have, I'm going to store the error. The error is, by the way, the error between my first guess and my guess afterwards. So I have my current grid, and then I update it once. And there's going to be an error between consecutive iterations. And I want to iterate until that error, so the difference between before this and after this is small enough so that it's stopping updating. And once it stops updating, that's a good sign that we've reached the final solution. So I'll just store those errors. I'm going to go for 2,000 iterations. All I do is in each iteration, I get my new updated grid, and I just convolve my old grid with the kernel that I have above. I set mode equals constant. That deals with boundary conditions, but we're dealing with boundaries on our own, so we don't really need to worry about this. Then I apply the Newman boundary conditions, which is the derivative is 0 at the insulators. And I just call that function. So my grid updated is Newman of grid updated. So it takes this array, sets all the derivatives equal to 0 at the boundaries, and it returns it. So I get my grid updated like that. I also have my boundary Dirichlet boundary conditions. So this says that at the location of my two plates, it's equal to 1 and equal to 0. So even though I do that whole averaging procedure, still at the end, I'm saying, no, this plate is always equal to 1. The other plate's always equal to 0. And I'm also saying at the boundaries of the box, the derivative is always equal to 0. So I do the averaging procedure, but there's still these locations of my problem where I enforce these conditions. And that's what's sort of super important. Then I append something to my error array. So I take my grid minus my grid updated and square it. So that takes the square of all the voxels, the difference between them. So this is a 3D array, the squared. And I take the mean difference between them. So this is the mean thing. So mean squared error here of all the different voxels in the array. And I append this to my error. So the error is really the mean squared error here. And then I finish my iteration and my grid becomes my updated grid. And then I go on to the next iteration. That's a pretty common thing. And so I can run this. It takes pretty quick to run actually. And you may be wondering why I'm not using numba here. Now you could use numba to solve Laplace's equation. I have a video on that. But numba won't work with this convolve function. It isn't able to convert it into C++ code or whatever it does. So this is a way where, well, there's only 2,000 iterations. So the for loop isn't the limiting factor here. The limiting factor really is this convolve function. And you'll see that 2,000 iterations on a 3D array, that's 1,000,000 times 2,000. This is 2 billion individual things that we're doing here. It is, you know, pretty significant, and it runs and it's done, so pretty quick. And then what I can do is I can look at my final grid. So I'm going to take the 50. Remember, it goes from 0 to 100. So I'm taking slice 50. And I'll look at slice 50 in X and slice 50 in Y as well. And it should be the same. So I can plot this. And you'll see that this is the potential between the two plates. So in the center, it looks like infinite plates, right? It's just the potential just decays like this, and the electric field, which is the gradient of the potential. By the way, if you want to know what the electric field is from a contour plot, you just connect a line between these contours, and it's always perpendicular to the contours like this. So in the center, the electric field is sort of like this, but then you also have the fringing field where if I always make my line perpendicular to these lines, it kind of has like a hemisphere sort of look, or a half circle look where it goes like this. And I should get the same thing if I take a slice in X. So that's actually a slice in Y. This is my slice in X. They do sort of the same thing. But I can also go off axis a little bit. So maybe I'm at the edge of the plates. So maybe I'm at slice 30 in X. Then what does it look like? Sort of similar, right? Maybe I'm actually outside my plate. So maybe slice is 10. And you start getting some interesting looking behavior here, right? Where now, like, even though these plates are shown in red and green here, I'm actually in front of them in the box with my slice, and you sort of get this pattern here. So it's very interesting, these things here, and I've sort of labeled the contours as well. And there's numbers here. Maybe you can't quite see them in the video. But, oh, and this label here should be Z over Z naught. And the other one is like X or Y. So this is in the Z direction. This is the Y direction. And you get this beautiful looking plot here. And as you can see, as confirmation that the Newman has been done properly, you see that the contour lines are always intersecting perpendicular to the insulator. So what that means is that, you know, there's no gradient in potential along these lines, right? And these lines are constant potential. So these constant potentials sort of go out like this. That means there's no perpendicular electric field entering into the insulator, which is exactly what we wanted. So we were successful. So finally, we can plot the error. I'm going to look at the root mean squared error, which is, I'm just taking the square root of the mean squared error, what we have above. New is the updated array. So I can plot this error, and we can see what happens throughout the iterations. So initially, and this is a log or a semi-log plot, by the way. So it's exponential on the semi-log, so it decays really fast. It starts getting good really quickly. and then it goes like this, and then it starts going like this and this and this, and you can see that we still have room to do better. So it still hasn't reached its optimal iteration yet, and we can go for more and more and more iterations. And the way to sort of modify this code, and I'm not going to do it in this video, it's more of an exercise and something you could think about, is if I had, say, instead of specifying the number of iterations, I specify an error. What I would do is I would use a while loop. I would calculate the error between these, and I would say while the error is greater than my threshold error, which is, you know, the error that I want, it would just keep going and going and going until this plot reaches a threshold error, maybe 10 to the negative 5 or whatever. So maybe it's like 6,000 iterations. Keep updating. And then once it reaches that, stop. So that's how you sort of modify this, where rather than a given number of iterations, you would specify a given error that you want, and that sort of determines when you stop iterating. So what I'm going to do is I'm going to show this error next to what happens if I give a worse initial guess to my array. So I'm going to say error 2. I'm just going to save this as my original error. So that's this here. And I'm going to rerun this with a not so good initial guess, and we'll compare the error rates. And so what I'm going to do is, rather than setting the grid like this, I'm just going to leave it as all 0.5s, and we'll see what happens when I get my new error, and I'll plot them next to each other. So I've reran them, and so I have my good guess in blue, right? And I have my worst guess in green. And you can see that when I give my good guess, which is where the potential sort of decays from left to right, I reach a lower RMSE much, much, much faster. Whereas with my bad guess, where I just said the potential is constant everywhere, my initial guess for the state, it does not decay as quickly. So this is sort of the important thing, where you have to give a good initial approximation, or the better that you can do for your system, the faster this will converge. And of course, that's less computation time. So if you have a complicated problem, it's a good idea to get an sort of estimation of, well, what do you think the potential would sort of look like? In this case, we have 2 plates. I know the potential is going to decay from left to right, so I could give an approximate good guess. But with a bad guess, it really would take a lot longer. And for this curve here to reach this value here, you could imagine that it might take, 10,000 or 20,000 iterations. And we could do better than my initial guess as well. In fact, you have 2 plates here. You can imagine the potential sort of decays to the left of the one plate, and then the other plate as well. So even my guess wasn't great. So you can play around with that as well and sort of see how it makes a difference. Anyways, I hope you enjoyed this video. If you made it to the end, you're a real player. I appreciate you on this channel. Be sure to join the Discord server as well. And I'll see you next time.